All right. So again, sorry for the interruption. So we were discussing the introduction of this tutorial, and I was talking about the Flory theorem. So here it is. The idea is the following. If you take a melt, so a polymer melt, is a situation where you don't have any solvent, and basically you have plenty of polymer chains that are all entangled together, like that, okay, whatever. And I will focus on one particular polymer chain, which is the one in the middle. Of course, this is a complex problem because all those polymer chains, they interact together. You have those repulsion and attraction interactions between the monomers. You have the solvent, but here there is no more solvent. It's mostly the presence of the other chains that matter. And so it's a very difficult situation. But there is a kind of screening mechanism that I would like to highlight, and that is called the Flory theorem. So if I now plot the concentration of the red species. So let me plot on one axis, for instance, this guy. This is space in this direction, and this is concentration. For the red part, what I see is that I see typically an increase of the monomeric concentration. So this is a monomeric concentration. However, for the let me just shift it for clarity, but it should be homogeneous. I mean, the same order of magnitude. Let me now plot the concentration of the black part. And since there is a depletion of black units because of the presence of the red chains, you have a negative a depletion of the concentrations. Okay, I've just shifted for clarity the two, but the plateau should be the same. So now, if you remember that the energy of interaction for one monomer, so it's called U in the Flory picture, well, it's typically given by, remember, it's kBt as a scale. Then there is the excluded volume parameter, which can be a function of temperature. And then it's proportional to the concentration of monomer, the total concentration of monomers. So this is the energy of interaction that any monomer that you put in the system will fill, all right? So it's proportional to the concentration. So now I can compute the energy per monomer, again as a function of space. Well, basically, you immediately see, and again, there is an arbitrary shift for clarity, but you have this. And thus, immediately, since this system is a dense system, meaning that you have the same properties everywhere, it's homogeneous and so on, it will imply here that the sum of those two is equal to the density or the concentration of your homogeneous material, and thus it is a constant. So this is kBt times excluded volume times constant. Simply because those two compensate. And so what is the conclusion according to you? In particular, we immediately see that there is no dependency anymore on number of monomers or size of the chains, in contrast to what was present previously in the concentration field. So what is the conclusion? What is the statistics of the red chain? And in fact, any of the black chains as well.
We go back to a Gaussian statistic?
Any idea?
We go back to a Gaussian statistic?
Well, the interaction energy is itself a constant. So it's zero if you wish. We don't care about the value of the constant. All the properties will be obtained by derivatives of that. So in the very particular case of a melt, there is a screening of the interactions. And this leads to the ideal chain statistics. This is an important result. We already found for solution, semi-dilute solutions or dilute solutions of polymers, that by carefully changing the temperature, there was a very specific temperature called the theta temperature, for which the chain became ideal in terms of statistics. But that was very particular. You had to take a solution and really choose the good temperature and the good solvent. Now we are saying that any melt, okay, any assembly of polymer chains, a very complex system, plenty of interactions, entanglements, and whatever you want. In fact, there is a screening effect that we just described that leads to the fact that this is also described by Gaussian statistics. So the result that is that the typical extent end-to-end radius of your polymer chain is really proportional to the square root of the number of objects times the size of a monomer. And this is really important. So the Gaussian statistics is in fact very realistic for this situation because melts are everywhere. You take a plastic material and you make it go above its glass transition by just melting it, well, you will get a melt. And this is described like that on the macroscopic scale. All right, so this was just an introduction on the Flory theorem. Let us start now with the blob concept. So now we are dealing with solutions, okay? So we have an assembly of polymer chains. This is, for instance, a dilute solution. You have solvent everywhere, but the chains are typically quite separated. So they don't fill each other. Each of these chains is described by the Flory radius, and we will assume that we have an athermal solvent, meaning a very good solvent. So typically we have the Flory exponent in 3D times A, okay? And the spacing is larger than that quantity, so this is a dilute case. In contrast, when you start to increase the density of polymer chains, at some point they will start to overlap and you enter what we call the semi-dilute situation. And in the semi-dilute situation, typically what you have is plenty of chains that start to fill each other, right? So let me just draw a typical network that it will resemble. This is the semi-dilute situation, okay? Of course, there is solvent everywhere. So what is interesting is that on average, there is a typical scale that appears in semi-dilute solution. We call it Xi, which is the scale below which a certain polymer chain, like that, for instance, doesn't fill the neighbors. You know, here you start to fill a neighbor because you are creating an interaction, I mean, short range interaction, but otherwise, in the middle, you only fill solvent here, okay? So basically, you are back into a dilute situation within the Xi scale. Above the Xi scale, well, then you are now into this mesh, this assembly, where you have, I mean, the long range properties of the polymer chain. And so what has been done, and proposed by Dejean in particular, was to say that, well, in fact, we could group the portion of the chains into what we would call blobs. And you can do that for any of the polymer chains. For instance, this one is also made of blobs that are units with this scale Xi, inside which the chain is completely free and in a dilute situation, okay? Above which you start to describe the chain as an assembly of blobs. So it becomes a renormalized chain with renormalized monomers, okay, that are the blobs. And an important feature is that if you start to pave the space with those blobs, okay, in a semi-dilute, you end up with a picture that is really, let me just rescale those big blobs becomes the monomers. Well, in fact, what you end up with is something like a melt of blob chains. Okay, so a semi-dilute solution is in fact a melt of blob chains. You can see here there is no more space, provided that I just replace all the monomers by those bigger units. I can just pave completely the solution and there is no other space. So the chains themselves are really only the only stuff present, okay? And so you are in a melt situation, which means that you can use this feature. You can invoke the fact that there is a screening, okay? And so therefore, what you would say for those blobs is that inside a blob, meaning, sorry, up, length scales smaller than Xi, you have semi-dilute, dilute properties. okay, or flowy. Outside blob on the long scale, now you are much bigger than Xi. Then it's a melt of blob chains. And so you have the Gaussian statistics. Okay, so Flory at small scales and Gaussian at small scales. And so you are able now to make a complete crossover between the dilute situation and the melt by progressively adding some material and changing Xi, the size of the blob. Okay, so that is the essence of this blob picture for the semi-dilute solution. And so we will now try to explore that idea. Okay, any question on this concept? No? Okay, so let us start. So in the tutorial, the first thing we want to do is to calculate the monomeric fraction, the minimal one, above which you start to fill some blobs or some other chains. Okay, so basically this happens when this is RF, when you start to really have chains that are placed every RF. Okay, this is RF and so on. And so dilute is when they are separated, semi-dilute is when they are intricate, and then you have the onset, phi star, it's the volume fraction, at which you start to feel the connection with other chains. And so this volume fraction is simply the properties of what happens inside one chain, because then it's really replicated completely into the solution. So you have n monomers, each having a volume A cube divided by RF to the cube. And so this is n divided by n to the 3/5 to the power 3, so to the 9/5, which is n minus 4/5. Okay, so this is, above that concentration, you will start to fill other polymer chains, and below that concentration, you will have a dilute situation. You can also discuss the melt. Okay, so this is the critical one, the threshold between dilute and semi-dilute. And the melt is when phi is equal to 1. Then basically, you are full of monomers everywhere. There is no more solvent, so the volume fraction should be 1. All right. So now let us consider one blob. Okay, again, the picture is the following. We have a blob, and the question is how many monomers do we have in one blob? Any idea on that? What is the statistics inside one blob?
It's the Flory one. No?
Please again, there is a problem of microphone, I guess. Let me open that. It's Flory inside the blob, okay? So you're right. So it means the size of the blob, Xi, should be given by Flory. So you have the number of monomers, this is the number, okay? To the power 3/5 times the size of one monomer, okay? Because we have Flory statistics inside one blob. So this allows me to say that the number of monomers per blob, G, is Xi over A to the 5/3. Another, okay, so if you have a microphone, yes, that's exactly that. So if you have a microphone, please interrupt orally. I know some of you don't, but it's easier for me. All right, so we know the number of objects, monomers, that are inside one blob. That will be a useful quantity in a minute. Now we would like to express Xi in terms of the volume fraction. Okay, so how can we do that? We should be able to connect G and the volume fraction in particular. So we already have this first relation that there is a link between Xi and G. And so what is the volume fraction for a semi-dilute solution? Well, remember, we are paving the solution with blobs. So if we understand the property of what's going on inside the blob, we understand the properties of all the solution because blobs are independent objects. And so inside the blob, you have how many material, how many monomers? You have G monomers, all having a volume A cube, and it's a volume fraction. So you would like to divide by the size to the cube of the blob. So this is the volume fraction inside the blob, and since it's repeated, it's the volume fraction inside the solution at any concentration. All right, so you can write that, and you can remember that G is itself provided by psi over A to the 5/3. And then you have 9/3 minus 9/3 as an exponent. Okay, so this is psi over A to the power minus 4/3. So I can take the invert of that, and so psi is equal to A 5 to the minus 3/4. So I have a connection between psi and phi. So we can examine some asymptotic limits for that. So first of all, the melt. Well, melt is when phi is equal to 1, which implies that psi is equal to A. So in a melt, the blob is reduced to a monomer unit. Well, you are left with the picture that you are really having real monomers. And so in a melt, you have plenty of chains like that everywhere, no more solvent. And so a blob, which is the unit below which you don't fill the other chains, is the minimal size of the problem. It's the monomer. Now, if you are at the critical concentration, so it's called phi star here, then remember phi star is equal to n to a certain power, minus 4/5. And so psi is equal to what? We have A phi minus 3/4, so it's n minus 4/5 to the power minus 3/4. Okay, and so it's A, and then you can remove the minus, the 4, so n 3/5. Conclusion, it's the Fourier radius. So now at the opposite limit, when you start to really increase the size of the blobs, meaning there are less and less monomers, okay? At some point, at the critical concentration between dilute and semi-dilute regimes, well, a blob is the full chain itself. So it's a very interesting mapping, because now it says that, in fact, a polymer solution can be viewed as an assembly of, as a melt of blob chains. This is one, okay, but in fact, the real chain is like that inside. All right, whatever it is. And you have plenty of other chains that do exactly the same. That can really, this is another example of another chain, right? Inside each blob, well, you have solvent everywhere. Same for any of those. And so I can pave the full space with those renormalized chains. But what is interesting is that by tuning now the volume fraction, if I increase the volume fraction, I will simply reduce the amount of solvent and reduce the size psi progressively. So psi will reduce. And at some point, I will end up to a pure melt with psi being equal to the monomer side. So in fact, this is a very elegant idea, this blob concept, because in between the dilute regime and the melt, everything is self-similar. You can just, it's always the same object that I've just drawn in front of you. It's a chain, it's an assembly of chains made of blobs. Only the blob property is changing with the volume fraction, but basically you have the same property as a melt. That is a very interesting feature. Okay. So now let us think about the main quantity in polymers here, which is the end-to-end radius. So what is the end-to-end radius then? If you understood this picture, how should I describe the typical extension of that red polymer chain, for instance, on average? We are in a melt of blob chains. So what is the size of those effective chains? Any idea? Remember the Flory theorem. We can describe this as a Gaussian statistics. All right, so since it's Gaussian, it will be the square root of the number of objects times the size of the effective monomer. So the number of objects is the real number of monomers, but divided by G, the number of monomers inside one blob. So I have this quantity. Inside, you have the number of blobs in one chain, okay? And you multiply this by an effective monomer size, which is psi, the size of a blob, all right? So this is, I can just rewrite it this way, square root of n, I can introduce a and just remove it here. And then I have 1 over square root of g. And remember, g is a function of psi here. It's psi over a to the 5/3. So psi over a, and then you have 1 over psi over a to the 5/3, 1/2, so to the 5/6. Therefore, you end up with this relation. It's psi over a to the 1/6. And beside, you know, a connection between psi and phi, the volume fraction. So this is, the volume fraction is appearing here. Psi over a is phi minus 3/4. So you end up with the relation that the end-to-end radius is typically square root of n, a, psi to the minus 6/424 minus 1/8. This is a result that is attributed to Daoud. It's a very elegant result because it connects all the range from dilute solutions to melt. We can check that now. So let's look at that. So R, I just rewrite it here, is a function of the number of monomers, the size of a real monomer, and the volume fraction of monomers. Look at the melt situation. Melt is described by phi of equal to 1. So R is equal to square root of n times a. Good. In the melt situation, we recover the fact that the end-to-end radius is provided by the ideal statistics with real number of monomers and real monomer lengths. And the critical point between dilute solution and semi-dilute solution is when psi star is minus n minus 4/5, if I remember correctly. Let me just check. Yes, 4/5. Therefore, it implies that R is square root of n a, and then you have phi, so n minus 4 to the 5 to the power minus 1/8. All right? And so therefore, this becomes a power which is it's 1/10 with a plus. And so it's 5/10 plus 1/10 is 6/10. And so it is 3/5 a, which is the Flory radius. Good. In the other extreme, we've recovered the fact that the end-to-end radius should be the Flory radius. So you have, for dilute solutions, a Flory scaling, for melt, a Gaussian scaling, and thanks to this blob picture, you have a full crossover in between with a situation where you don't have a real power law, but you have a crossover, a smooth crossover. Okay, that's the beauty of the blob concept. And the reason I'm introducing that to you, it's because we will use it to describe the invasion of a pore in a minute. Okay, so before thinking about a real pore where a chain is going inside and looking at the statistics and the flux, what we would like to do first is to take a step back on the side, if you want, and we would consider an equivalent or analog problem, is the following problem of a chain under traction. Indeed, if you take a polymer chain and start to really pull on it, this is typically what you will get. If you pull not too strong so that it's not fully extended, you will start to progressively elongate the chain. And what we will discuss in a minute is that, in fact, you can see that everything is as if your chain was mostly a linear assembly of blobs. And we want to define the size of one blob, and it will be related to the force and also to the temperature, because we are here dealing with a solvent at a certain temperature. So we are in a canonical ensemble and so on. Okay? So that is the idea. We would like to draw a connection between confinement and pulling on the chain because of the extended assembly, if you wish. And this is a work that has been performed by Pincus in the US, in Santa Barbara. All right, so let us start. So first of all, let us list the typical sizes of that problem. So first of all, I start with one. It's a really a dilute situation. I'm in a dilute case now. I have only one chain, if you want. And it's a good solvent and even athermal solvent. Good athermal. So the athermal situation is the simplest one. The Flory radius is really connected to the size of the monomer. There is no more excluded volume. In fact, the excluded volume is a monomer volume itself. Okay, so this is the ideal situation, if you wish, for realistic chains. So we are dealing with that. So of course, there is one first important size, which is the typical extent. And I will assume that we are doing the limit where the size of a monomer is going to 0, the number of monomers is going to infinity. And so A is not a real length scale. We don't consider this as a length scale of the problem. We are really in the continuous description now. So the reference length scale is RF. But now I've pulled on it. So now the chain is more like that. So I can kind of define another length scale, which is the typical extent. And a proper definition would be, for instance, the norm of, let's say, the average radius. So that this guy is 0, the end-to-end radius as a vector is 0 because you have the same probability to be in one direction or the other when there is no force. So good. It will start to be non-zero when you start to pull on it. So this is, in fact, the main observable that characterizes the extension, second length scale. And finally, you have the force. And to construct a length scale, we are in, so this is one length scale. The third one is, if I do a ratio between the thermal energy and the force, this is the typical length scale associated with the force that I can construct. And so let me call it D. And this is the only 3 length scales I have in the problem. The undeformed size, the deformed size, which is my real observable, and the amount of force versus thermal energy, okay, in a sense. So this defines another length scale. Okay, so let me see. So now we would like to consider a typical law for the extent length. And so it should be, as we just said, a function of RF, a function of the force I'm pulling, and the force in terms of what? Well, KBT. So in very general terms, by dimensional analysis, I'm expecting the length to be a function of the initial radius, the force, because I'm pulling on it, and the fluctuations induced by the temperature. And so in scaling analysis, here I have 4 variables and length, force, so 2 units. The final one being a combination of the 2 previous. It's force times the length, so it's not an independent unit. So you have 2 independent units. All right. So you are left with 2 from the pi theorem. or Buckingham theorem, you are left with two dimensionless group. And thus, I can, for instance, look for a relation that is of the form L divided by RF. That is the first dimensionless group I can construct. That should be a function, let me call it H. It's an unknown function of RF divided by D, where D has been defined as KT over F. So this is a very general relation by dimensional analysis. And the question now is to look at the low force limit, low force regime. So low force means, let me write it here, H is a function of RF, D is KBT times F. So the low force limit is when F goes to 0. So when the argument here is vanishing, it's going to 0. That's the low force regime. Therefore, I can do some Taylor expansion of that. So I'm looking for something like H naught plus H prime naught times the vanishing constant here, which is RF variable, sorry, which is plus etc. So according to you, what is the first term here? This guy. When there is 0 forcing, what do you expect for L? Or this guy?
It's 1.
Which is the extent. 0 forcing.
With no force, we should have 0, no?
Any idea?
Do you hear me?
I'm not pulling on the chain. So what should I find? Let me look at the chat. No, I don't hear you. I don't hear you. Okay, so someone answered probably. So let me give the solution. So of course, as I guess you've all understood, if I don't pull on the force, there is a 0 average radius in terms of vector. Okay, and so I can basically kill that term, and I'm left only with the first term. So in terms of scaling, no matter this constant, it's typically RF, F, KBT. This is the linear response, and I will neglect the higher orders here. So I end up with the fact that L, I heard someone. Is it Leo?
Oh, no, yeah.
Yes, I can hear you. So I hear someone, okay? I heard someone. Anyway, RF squared.
Sorry, can you hear me?
Yes, perfectly.
Okay.
Thanks.
Why is it not 1, the first thing? Like when we do not apply force, shouldn't L be equal to RF?
So be careful. What I didn't define it this way. In that case, the norm, of course, this is non-zero typically. It has a certain extent. But what I did here is very different. Here, I averaged the vector and then took the norm. So if there is no preferred direction, this should be 0 as a vector and the norm is 0. Why did I make this choice? Because I want to characterize the elongation. So this is something directional. So I want to create some kind of observable that tells me if there is an elongation with respect to that situation. Do you understand?
Yes. Okay,
so this is really the observable that would tell me, well, I'm elongated or not. So when I'm not elongated, this should be 0. So this is reasonable to define it this way or with a prefactor if you want. All right, so we are left with the relation that RF squared, the force, and divided by KBT. And so we end up with the fact that the relation is, So the square root of 3/5 is 6/5 f a over kbt. So the extension of my chain is 0 when there is no force, and it increases linearly with f because I'm at small f. That is why you have a linear response. Okay. Of course, we might expect non-linearities if we go at very strong forcing, and we will see that in a minute. So it's interesting. There is a comment to be made. Look at the power here. 6/5 is greater than 1, which means it's a superlinear behavior. In the sense that now I'm really pulling on my chain, and I'm saying that if I double the number of monomers, so really, I'm really do it quickly here. I'm simply doubling the number of monomers. Well, I don't double the length; it's even more. Any intuition why it's the case? For those of you who have a microphone. Why is it superlinear?
Because when we pull on the polymer chain, we don't eliminate the repulsion between the monomers, and there are more monomers, so
Exactly.
There's a bigger excluded volume.
That is correct. So in a sense, if you compare that to the ideal case, let me just write the ideal version here. The ideal version would be L0 for ideal is R0 squared F over KT, and this would be indeed, due to the square root, linear with the force and the number of monomers. Okay, that's the ideal version. And there, the intuition is, well, I double the number of objects, well, I double the length. That's clear. But as you correctly noticed, now we are in a realistic situation where we have excluded volume interaction. And thus, well, we have to remember that those guys, they talk to each other. Those guys, they talk to each other. So you have transmission of the force, not only along the backbone, but also in between monomers. So if you want a non-local interaction in this vision. And so it should be more extended than what you would expect from simple linear analysis. Good. Well, so this is the not very interesting situation. In fact, what I've done, is to take the Flory radius and marginally extend it, pulling very gently on it. So it's kind of ellipsoidal, but marginally, right? It's a linear response. So I don't really get a picture where I have fully extended chains like in a tube, like in a confinement situation. So this is what I would like to look at now. Now, I assume that I have very large forces. Of course, the forces should be not too large so that I still have some statistics. It's not a fully extended line, so I will still assume that the force is large, but it remains smaller than KBT over A. Okay, we will understand that in a minute, but I assume that it's not too large. And in that situation, well, I can really describe the assembly as something which is pretty elongated. Sorry, no crossing. Those are not real crossings. Think outside the plane because we have excluded volume interactions. And so what is interesting is that it resembles an assembly of blobs. Each blob is typically of size D, which is KBT over F. Why? Because D is really the distance below which thermal motion dominates and above which macroscopic forces dominate. Think about DNA as well. Think about macroscopic examples such as, for instance, a telephone coil. So you know the old telephones from your grandparents, there was a cable between the telephone apparatus and the central machine. And it was something like a cable with stuff like that, features. And what you can do is to pull on this telephone coil, and you will localize. The more you pull, the more you localize the feature. So there is a typical distance inside which the pulling has no effect. Really, it does its own bending physics. But on larger scales, I mean, you can really flatten it. So you are stronger than the microscopic physics, if you wish. So it's really an analogy. But what is interesting is that before we were dealing with dilute solutions and then semi-dilute solutions. And so when you deal with semi-dilute solutions, you have average crossing between the chains in the solution, which naturally defines psi, the size of a blob. Now I have only one single chain, but I have a force that pulls on it. And this force, compared to KBT, provides me a typical length scale that defines a blob. Again, a blob will be defined the same way as before. Inside it, it's an unperturbed feature. I mean, it will do its Flory-like behavior. But above that, well, you see that you have a linear assembly of objects. So the force is dominating. It's really aligning the blobs in a linear assembly. Okay. So the very nice argument, I will do the scaling, but it has been calculated more thoroughly by Pincus, is the following, is that the typical size L will be given by the number of objects, blobs, times the size of one blob, G. And this gives me immediately the force displacement or force deformation relation, because in D, there is the force. So what is the number of blobs? Well, it's the real number of monomers divided by the number of monomers inside a blob, and D is still here. So we have to remember the blob picture. Inside the blob, you have the Flory behavior, so D should be G to the 3/5 times A. So it says that I have G, which is D over A to the 5/3 times D to the 3/3, if you wish. Okay, so I can simply multiply everywhere by A and divide by A. So it's typically NA, and then you see you have A over D to the 2/3. So by this very simple blob picture, you end up with the fact that L is the fully extended version corrected by a factor that depends on D, where D has been already identified as KBT over F. So several comments can be made. First of all, L is much smaller than NA, because we assume that small a is much smaller than KBT over F. So A over D is much smaller than 1. So of course, because if we start now to pull fully on the chain, you cannot draw this blob-like picture with some statistics inside. You will have really a fully extended line, and that's all. Okay, one configuration and no statistics inside. So you want to let some polymer statistics with a sufficient number of monomers inside to have this scaling. That's the first part. The second interesting aspect is that it seems to be linear with N. There is no dependency on the number of monomers in D. So L is linear in L, which means that when you are in this fully extended picture, if you double the number of monomers, you will simply double the length. This is due to the fact that those blobs are independent. This is the definition of a blob, in fact. Okay? A blob is the maximum, or if you want, the maximal size above which you have independence of the properties of the chain. Either because you are screened by some Flory-like interactions, or here because the thermal energy doesn't play any role anymore. So you end up with L is linear in N, sorry. Let me just correct that. Which is a feature associated with the fact that blobs are independent objects. Finally, you can just put back the force inside this expression and end up with the following expression, which is A KBT F to the 2/3, and then I can just rewrite it the following way. F is equal to KT over A times L over NA to the power 3 half. So it's not linear anymore. FL is not linear. So we have indeed gone beyond the linear response, and we found the non-linearity of the problem. That is normal, is a limit where we are really putting a lot on the system. And there is an exponent 3/2 that is reminiscent of the Hertz exponent. If you indent with a sphere an elastic material, well, the force indentation law will be typically 3/2 as well. So we call often this quantity Hertz-like force indentation law or force elongation law. All right? All right. Now we would like to discuss about entropy a bit. So we are at question number 4. Okay, so the entropy, let's not talk about the entropy, but the entropy reduction. So this is the entropy reduction with respect to the situation where you don't pull on the system. So you know really the entropy, but then what you will do is you pull on it, so you will start to elongate, so you will reduce a lot the entropy because you will restrict the number of conformations more and more. And so we are interested in this variation. How much do you reduce the entropy? So we can write it as a function. We can put a minus sign after, but a function of, let me call it h. It's another function from the previous h, okay? So what should it depend on? So let me also normalize it by KB so that it's a dimensionless quantity. So what sizes should it depend on? We have the same as before, right? So we have the initial size, the final one under the action of the force, and a priori we have also the force scale. However, forces are related, I mean, forces, external forces, not entropic forces. Forces like F, the operator's force, the work, is not included in the entropic description. It's more an enthalpic or energetic aspect. So we can be sure that there should not be any effect of the force here. Of course, the force will elongate the chain, and since it's elongated, then you have a certain size. So here, this will tell us or play a role in the configurations. But the force itself cannot appear in the entropy. It's a different concept, as you all agree, I guess. So we end up with the fact that delta S is some function, and I can put a minus sign because I want a reduction of entropy, so it doesn't change anything. But I can say that it's typically minus KB times some function of RF, or even let me write it the opposite way. It doesn't change anything, but okay. By dimensional analysis, again, you have two arguments that both are lengths. So if you count the number of dimensionless group, it's 1 for the variable. So you have only one dimensionless group. The only one I can construct is this one or the opposite or any power of it. All right, and now we will assume, and it's an assumption, that we enter in a scaling regime. So then it should be something like L to the RF to any power alpha. That's what we are looking for. The minus sign is indeed saying that, so if alpha should be positive, so that with the minus sign, when L goes to infinity or grows a lot, at least, you reduce a lot the entropy, so delta S should diminish, okay? But I don't know alpha. I just wrote a very general relation. But it's interesting, I know delta S. So I can construct delta F, which is the variation of free energy, which is the work minus KB minus T delta S, plus the work, which is the work is provided by what? By, let me even clear that. This is macroscopic. I want to keep macroscopic variation here. The work, we already wrote it. Oh no, we didn't write it, sorry, but I will do it now. I will say it's basically simply force times elongation. That's the typical mechanical work if I'm pulling on an elastic stuff. So apart from prefactors, and this is all scaling, well, the equal symbols here, I have kBt times a certain power of L over Rf minus Fl. And so at equilibrium, this delta F should be minimized, right? So I can say that the variation with respect to L is 0, which implies, and I will take another blackboard, that alpha kBt L alpha minus 1 over Rf alpha should be equal to F. In fact, there is a minus F, but I put it on the other side of the equality here. Okay, so in scaling, I forget the alpha here. It's a scaling discussion. I end up with a force relation that is conclusion. What should be the value of alpha?
It should be 5/2.
Correct. Indeed. This then tells me that I have kBt times L to the 3/2 divided by Rf to the 5/2. So Rf is n 3/5 a to the power 5/2, which is kBt over a L to the n a 3/2. And that's it. All right. And this is exactly what we found F before from the argument with the blobs. You remember we had force kBt over a L divided by Na to the 3/2. So the only way we recover the good value of the force is when we choose indeed alpha is equal to 5/2, which was your intuition. Good. So now if F is equal to that, it means that F, the work in terms of scaling, is minus Fl. So it's kBt, I forget the prefactors, the minus in particular is L to the 5/2 divided by Na to the 3/2. And that's W. And if I consider this part, minus T delta S, is also written this way, right? So I have, where is it? Up. Let me write it here. I have the fact that typically delta F, when we are at the minimum, is kBtL Rf to the 5/2. Okay, you sum the two terms, but they have the same scaling. Okay, that's something we will discuss later. Let me just mention a fact. This was never checked. I mean, experimentally, this relation here with alpha is equal to 5/2 was never checked. Alpha is equal to 5/2 because this is what we found, but this was never really verified. Okay, so, but we will discuss in a minute that this equation for the free energy with L to the 5/2 is recovered in confinement. So we'll make a connection, and so it's very likely that the entropic expression is correct. All right, so now let us discuss the confinement energy. So now we change a bit the situation. We are not anymore pulling on a material, but we consider a tube channel, and inside which you have a chain at equilibrium. Okay, so no more pooling, but a certain size that appears, which is the size of the channel. And naturally, since now, so remember, so far we did the semi-dilute solution, there was a natural length scale for the blobs, which was xi, the typical distance between crossings with other chains. Then in the previous example, what we did is to pull on the system, and so the force was defining a length scale when compared to thermal energy. Again, there was a natural appearance of some blob. And here, the natural length scale is D. So D will define a blob. Let me now say that on average, everything is as if I have a linear assembly of blobs. Inside this blob, well, the chain doesn't fill the wall. It's basically a florid chain. But as soon as I'm going on larger length scales, I have felt the wall, and so I'm forced to have a linear assembly of blobs. So it's a linear assembly of blobs. Okay, and inside each blob, you have flurry. So again, it's the picture. You see, the blob concept is in fact very general. As soon as you have an intermediate length scale in your problem, either from a force, from a confinement situation, or from the presence of other chains, then you define blobs. Inside this blob, well, it's an independent problem, as if the chain was alone in the solution. And outside, well, you have a constraint, and therefore you have either linear assembly or ideal random walk, as we discussed for the semi-dilute situation. And so the observable in this problem is, as before, what is the length? I want to know the length. The typical observable is the macroscopic size of my polymer chain. And before entering that pore, well, the reference length in the bulk was RF. That's the bulk reference. So the bulk is that, the confined situation is that, and it is characterized by L and the confinement length D. Those are all the length scales in my problem. All right. So let us now discuss the typical extent L of the confined chain. So according to you, what should I do to calculate L?
We just do same as before. We take the number of blobs, which is n divided by j, multiplied by the size of the blob.
Yes, exactly. So the number of blobs you told me is n divided by j, and the size of a blob is now d. And g, we should remember that is connected to d over a to the power 5/3, so that we recover the Flory regime inside one blob. So that is exactly that. And so I can just rewrite it NA divided by A to compensate. And then it's NA D over A once, and G, it's D over A to the power 5/3, which says that, as before, I end up with A over D to the power 2/3. Well, which is exactly what we got for the pooling situation that was here. This is the pooling. The only difference is that the confinement length scale was set by the force in the pooling, whereas here it's really a geometric confinement of size D. So it's capital D. But you have exactly the same limit. Again, it's linear in N. Again, it's much smaller than NA because I've chosen D so that it's still bigger than A, okay? Despite being much smaller than the size of the object that I would like to put inside, so that there is confinement. and you recover the 3/2 force elongation law. So it's exactly analogous, in fact. Okay, that is why we wanted to present you the two of those. So let us go on. Now, let's think about the confinement free energy. So the confinement free energy is, let me even, on the general aspect, will be a certain function h, another one, okay, it's another h. So well, of course, I should know what type of object I want to put in confinement. So this is the main information before any deformation. It will depend on how much I'm elongating it. And it depends also on the amount of thermal energy, because this is setting my anthropic constraints. So 1, 2, 3, 4 variables, 2 units, energy and length, and so 2 dimensionless groups. So F confinement is something like kBt times another function of sorry, why L? I should not even talk about L, it's D in fact. For my problem here, I have a certain polymer chain, I have a tube of a certain size, okay, and I have kBt, and that's what sets my confinement energy. L is another observable, and we will discuss it in a minute. So it's, what did I say? It's D here. So I have a certain power law if I assume power law assumption, okay? I'm looking at scaling regimes. Okay, that's a very general relation, and so it will be something like n3/5 A divided by D to the power beta. All right. So now we know that the blob are independent objects, meaning that if I double the number of monomers, I will double the number of blobs in this situation. And I should double the free energy because blobs are independent. So therefore, I know that n3/5 beta should be equal to n by independence of the blobs. Which means that B is necessarily 5/3. To understand this physics, let us do another example. Let's do, for comparison, the ideal case. So in the ideal case, the confinement free energy, F, is a function of kBt. Okay, let me call it 0, F0 confinement. It's kBt times, what do we have? We have same thing, so it's not RF, it's R0. R0 to beta prime, it's another exponent, divided by D. And now we have kBt times square root of NA over D to the power P prime, beta prime. And thus we end up with, if we assume that blobs are independent, beta prime should be equal to 2. So you end up with the fact that you have kBt. And in fact, you knew that this is true because we did the Schrödinger tutorial. I think it was number 5. We found in the ground state dominated situation where you have a chain that is ideal and that is very confined in a narrow slit, we found that the probability was something like So there was exponential minus the number of objects, a squared. In the ground state dominated, you were taking the first, okay. And I think there was a pi squared. Please check. I'm not sure about the pi or the pi squared here, but please check that to be verified by you. In any case, we don't care about prefactors. It was divided by 6 or 6 LX, I guess. Yes, something like that, and check the prefactor. Sorry, I'm not sure. But it was basically n a squared over d, if d is now Lx, right? Times kbt and divided by kbt plus a constant, and I don't care about the constant, okay? Times the constant. But basically it was a Boltzmann factor with a free energy that is this one. So it's kbt n a squared over d squared. So it's exactly that. So it's really reasonable to have something that is at the end linear in the ideal case. And so we have the same here. Basically now in the Flory case, which is a bit different, well, it's not a power 2 that you have to put, but it's a power 5/3 because blobs are independent. Okay, I hope you followed me with this. Anyway, we assumed that blobs are independent, and therefore we end up with the fact that beta is fixed to 5/3. So this is the confinement free energy. Okay, with prefactors. All right, so now let me go on. So we have the free energy. Confinement is, we said kbt, 5/3 of the confinement ratio. And so we would like to ask, what is the free energy of confinement per blob? Well, it's fconf of confinement divided by the number of blobs. And as you told me previously, this is divided by n over g. So this should be equal to kbt rf over d to the power 5/3 divided by n and multiplied by g. And g is what? G in terms of blobs, remember, g is d over a to the power 5/3, so that you have the Flory picture. And then g is, as I just said, d to the 5/3, a to the 5/3. Right? And remember, RF is 3/5, so the dependency in n vanishes, and the a 5/3 vanish with that. So it's a striking fact. The free energy per blob is kbt. So it's something you want to remember. Blobs are independent objects, and inside a blob, well, the free energy is kbt. We already recovered that when we were dealing with the free particle in the quantum box that was mimicking a polymer chain. And we calculated typically the free energy inside, and we thought, we found that the free energy of the full chain is kbt. Because the blob, in the unconfined situation, the blob was the full chain itself, and it has a typical free energy, which is kbt. In particular, I think we recovered the fact that we have the PV equal kbt, a law for n equals 1, ideal gas law for n equals 1 when we were studying tutorial 5. So we knew already that basically a polymer chain, its typical free energy is kbt. Now that we have blobs, and they define inside this, the physics is independent of any confinement. So inside a blob, you should have kbt. You have a chain, and it doesn't matter on the number of objects. You have KBT per blob. Okay, so that's a very important result, and in fact, this is the one you want to remember. All right. So now we have the free energy per blob, and we would like to compare those results to the ideal case. So we already discussed the ideal case, so I won't do it again. The ideal case is provided here. We just recovered tutorial 5 and saw that in fact we have R0 squared divided by the confinement length. So this is already done. But I would like to compare that to the traction problem, to the pulling problem. So let us see what is F. F is KBT, we said, RF divided by D to the 5/3. And this is confinement. But in the traction problem, what do we have? We have, sorry, it's at the end. In the traction problem, this is what we got. Delta F is KBT L over RF to the 5/2. So it doesn't seem to be exactly the same, traction or pulling. I think I said pulling last time, so let's keep it. So let us see if really they are different. Let us play with the second expression. So we have KBT. I remind you that L was the fully extended version, but reduced by some power A over D, which is to the power 2/3. Okay? Yes. Yes, 2/3, and this is why we add 3/2 as a force elongation law. Okay? So now I can branch that in the free energy, and so I have NA, A to the D to the power 2/3, and then I have N3/5 over A to the power 5/2. Okay, so I can play a bit with this expression. What do I get? I have N5/5 divided by N3/5, so 2/5, but with a 5/2 here, so it's N. Those guys, they vanish, and then I have A over D to the power 5/3. And thus I can put the N inside. So it's exactly, let me check, it's exactly that. Apart from the fact that D has been replaced. Before it was the length scale associated with the pooling, that was defining the blob, and now it's a real confinement. But in any case, it was not, this expression was not different. We obtained that from the entropy, if you remember correctly. It was not, in fact, different, despite the fact that we were introducing L and so. So it's a check that the entropy expression, as I told you before, is probably the correct one. Okay, so we are done with the statistics of confinement and the free energy of confinement. What we would like to do now to end up the problem is to come back to our initial discussion. I now want to consider a polymer chain that is really big, but I want to push it inside a small, narrow region. Either because I'm considering DNA inside a cell or inside a virus that wants to escape or invade some other place, okay? So you could think about that, like think about the COVID, for instance, and it has some DNA, and this long chain will enter some cell and will be replicated, and the genetics will be modified. So the expression of the gene, sorry. So we have this polymer chain that is entering a tube that is pretty narrow. As before, we call it D. And it is very unlikely that it does this alone, because as you remember from the probability I will rewrite it, sorry. Okay. As we remember from the tutorial number 5, the typical probability for having a certain object here confined, the whole chain inside the tube is something like, if I remember correctly what we just wrote, something like that. And so clearly, and sorry, this is for the ideal situation. We are also in a flowy situation, but just for reference, for just thinking a bit, we see that the probability is basically much smaller than 1. Because D is small, we are ground state dominated, and so this exponential is exponential minus infinity in a sense, or at least something very large. Therefore, it's very unlikely that if you take the DNA of a virus and you put it near a door, it will go inside spontaneously. It's very unlikely because of entropy. The chain doesn't like to be confined. It has a strong penalty if you think about the probability here. Okay, so the only way you can do that is by either adding a force, a pressure difference. If you think about a flux, you can think about osmotic pressures in a cell with different ionic concentrations on one compartment and on the other, so that it will push. Or equivalently, you can think about flux. So we can inside add some velocity of a fluid, J. Basically, when you are trying to recover some oil, you will push water, and so you can control the debit. And this is the debit that will be maintained in each of the pores, because the rock is porous. Okay, so G is important. Otherwise, it will never enter. So, but we would like to see how much should we need to push. How much money should I put into my motor that is pushing water inside the oilous rock, or how much energy the cell should be producing to ensure the ejection of DNA or any long molecule, or a virus to inject some DNA somewhere. So first of all, a bit of fluids. So what is the fluid velocity inside the pore? Well, J is defined as a volume per unit time. It's a debit, so it's velocity times d squared. If I forget the pi prefactor, if it's a cylindrical tube. So it says immediately that, well, the velocity of fluid inside the pore is fixed by the debit I impose outside and the size of the tube. All right. Now, I assume that I have penetrated with a length L. This is my variable, my observable. I want to push inside, so L will grow with time, but I would like to, for any L, to describe the situation, the amount of free energy, for instance, the penalty, the debit I should introduce. And so L is really my quantification of how efficient my invasion was. I mean, how far did I go? So L is the function, and you know, we should remember that inside confinement, we are in fact introducing a mesoscopic length scale. So there is a blob picture that emerges, and so therefore, I have natural blobs of size d. So if I want to estimate for such a configuration, what is the free energy or the excess free energy with respect to the situation where I was not entering the pore? Well, I have to remember simply that each blob is independent from the other and has a free energy, which is kBt. We say kBt per blob. That's the main message. There is kBt per blob, and therefore, the free energy of confinement, let me call it conf again, is kBt times the number of blobs inside the pore. And so the number of blobs is what? Well, it's immediately given by the total penetration length divided by the size of one blob. So it's L over D. Okay, I have the confinement energy. So the longer L, the higher the free energy, so the more penalty. We already knew that it's very complicated to spontaneously enter a pore due to entropy. You will pay a price that is increasing with the amount of things you put inside the tube. But there is a strategy, which is to put some flux. So now let us estimate the work the operator has to perform. So before that, I would like to calculate the viscous force exerted on a blob. On one blob. And I will assume that a blob, we know that in the static picture is something that is an independent object, and what matters inside is not connected to what happens outside. So on the static picture, a blob is a kind of sphere with his own cooking inside, but there is no effect of the outside world on the inside of the blob. Okay, it's an independent compartment. And so then there is an assumption, and I don't demonstrate that, it's quite difficult, but I assume that on the hydrodynamics, so on the dynamics, the blob is also an independent object. So it's an assumption. Blob is also independent, yes, independent of the outside. Oop. I will rewrite that. The blob is on the dynamical aspect can be viewed as a hard sphere with a size d. And therefore, the viscous force on one blob is typically Stokes, so eta v times the size. Okay, so I'm assuming that in fact, due to the screening, there is no hydrodynamic interaction inside the blob. It moves as a sphere, and I'm not demonstrating that. Okay, we will discuss that I think in the tutorial number 13, where we deal with polymer dynamics. But for now, assume that a blob is assumed to be a rigid sphere for the dynamics. And it's really an assumption. I didn't demonstrate that. Okay, so if you agree with that, if you assume it, then necessarily the typical force is Stokes, so viscosity, size, and velocity. Now, if I want to calculate the total viscous force, blobs are independent, also on the dynamical aspect, and therefore I have that times the number of blobs, which is L over D. I just multiply the previous force times the number of objects. So as if you had a bed assembly, like something you would put around your neck, for instance, a bed assembly, and you put that in water, and you try to drag it, well, you will pay Stokes price for any of this small bed, okay? So I just multiply by the number of blobs inside. All right, so there's a simplification going on here. D doesn't matter. But I can also transform V as, what was it? J over D squared to make it appear again, over D squared times L. Okay? And now I can calculate the work associated with this viscous force. The viscous work is minus the viscous force times the length inside the tube. Okay, so it's minus what we just found, eta J over D squared L. That's what we find. And as a consequence, we can calculate the total free energy which is the sum of the confinement penalty plus the work due to the entrainment by the viscous flow. And so the confinement one was kBT L over D, while the work is minus eta J L over D squared. So let me just recast this to a dimensionless way. And I can basically introduce rescale variable. So F tot divided by kBT is the reduced energy. The good variable is this one, L over D. So, and then I can introduce a typical, we see here that there is a typical flux that is appearing. So let me introduce it as is, kBT over eta. Okay, so that under this dictionary, I end up with a very simple equation. So in a mathematical description, the free energy, there seems to be a penalty, but there is a facilitation aspect. So I can now plot that. And let me rewrite it here. So it's J over JC, or yeah, J over JC, x squared. So if I plot the rescaled free energy as a function of the rescaled penetration here, well, it starts linearly, and then it should be a parabola. Okay, so we can just rapidly find the minimum. This is 1 minus 2j over jc times x, and so the extremum, not the minimum. So the extremum is for when this is equal to 1, so jc over 2j. And therefore the maximum is for jc over 2j, jc squared over 4j squared, so jc over 4j. All right, so what we have here is that we have a barrier of energy. If the system is not pushed, so x, remember it's L over D, and y is F over kBT. If the system is not pushed or not inside the pore, well, you have a barrier. So you have to pay energy to make the polymer chain go inside the tube. But at some point, if you are long enough inside the tube, then it's easy because you can really gain a lot of energy by being pulled by the flow. So there is a trade-off and a barrier to be overcome. And so if you want that to happen spontaneously, you want the barrier to be F of the order of kBT. If that magnitude is on the order of kBT, so it means that y, which is F over kBT, is of order unity, in fact. If that barrier is of order unity, then you will see pore invasion. And so a barrier of order unity means that you want JC over J to be of order unity. I forget the factor 4. So it seems you want J to be provided by JC typically. That is very interesting because it says that, well, you have to push with some water, okay? But JC is, look at that, it's KT over eta. Can you make a remark about that result? Why is it striking? This is the critical flux.
It does not depend on the size of the pore.
Yes, that is exactly that. It's amazing. It does not, in fact, something else, right? It does not depend on two things. It doesn't depend on the size of the pore, no matter the smallness of the size, doesn't change anything. It doesn't depend on the size of the object itself. I mean, you could think that, okay, putting a few monomers, why not? I mean, entropy is difficult, but you can at least put a few of them. But then putting the full chain, well, it would be exponentially decaying. If you remember that guy, for instance, with minus here, okay? So the penalty is really huge. But the outcome is amazing. There is a flux scale that appears in this problem, which is provided by entropy and by the viscosity of the solvent, okay? Only. And what is amazing is that this prediction by Dejean and Brochard has been checked. In fact, apart from minor details, really below JC, you don't see any invasion, and above JC, there is invasion. So that is very elegant. Let me finish by commenting on the fact that Brochard and Dejean call that a suction mechanism. Why? You have to remember that now we said that J is typically JC, right? So this is typically 1 or 1/2, okay? So X is equal to 1, apart from prefactor. It's of the same order of magnitude, which means that L is equal to D. So for having invasion of your pore, you need to put JC, but as soon as you have put that flux, it will allow you to pay that price typically, and then one blob will enter. So L is equal to D is one blob enters, one blob inside. As soon as one blob is inside, then you can just go down the potentials and then it goes. So imagine you have your chain, you push water, then there is one blob that appears inside the tube, and then by suction with the solvent, it pulls all the chain. So in fact, that is why it doesn't depend on the number of objects in the chain and on the size. What matters is the flux here. So that's the final result. And it has been checked and refined. So in fact, if you look at I mean the invasion rate or whatever, you can, let me just be very vague. Invasion as a function of flux. Basically, what people have measured is that instead of having something 0 and then boom, well, in fact, you have correction to that picture. Of course, look at all the prefactors I've forgotten and the assumptions I've made. But nevertheless, this is the critical value that still appears. Okay. So with that, we will stop here. Sorry, we're a bit late, but okay, we caught up a bit with the time. Again, my apologies for the problem with the pen. I will make sure it doesn't happen again. And if you have any question, please. Yeah. Floor is open for discussions. All right, if not, please do not hesitate to contact me by email, as you always do. And I wish you a very good weekend. And I will put that video on the Dropbox. Thanks. Goodbye.